Thanks, Michael. Hi, this is Samantha. I'm here at Re3D. Today I'm in our machine shop that we're still working on getting power to so we can use our CNC and refurbishing here in our Austin, Texas headquarters. And I'm joined by a couple of our teammates and so excited today. For those of you in the FGF User Group community, again, we'll continue to emphasize while Re3D has facilitated this, we look to so many of our peers, those that have gone before us and walking alongside of us that also have incredible research insights and hardware and perspective on printing with pellet and flake or FGF. So we're honored today to highlight one of those pioneers, in particular, Dyze Design that we've learned so much from and have admired. They're just north of us a wee bit in Quebec, and today we're honored to have Simon join us, who's their COO, and he has a really interesting background. Not only does he lead efforts at Dyze, but he also has background in web development as well as blogging and photography and communications. He hails from, I'm going to screw this up because I don't speak French. I should have had Annabelle do it on our team, Université Laval, where he has a bachelor's of arts. He also has some web development background at Treehouse. But more interestingly, I thought, in addition to his very broad background, is he's also a home brewer. So maybe at the end when we turn the Q&A off, we can learn a little bit about that as well, because it seems like he's a maker at heart, like many of y'all. But with that in mind, I'm going to turn it over to Simon and let him share about some of the amazing work that they're doing up in Canada and beyond with their community. And then we'll have a Q&A afterwards that'll be recorded. And then we'll turn it off for some internal collab for those that are here in real time today. Thanks, Simon.
Thanks, Samantha. So I'll just share my screen here. Just let me know if you're able to see that.
Oh, that looks good.
Yeah, perfect. Okay. All right. So very excited to be here today. And thanks again, guys, for inviting me. I feel this community is growing, and it's very good for everyone to have those meetups. And yeah, happy to be the April session here. I wanted to bring today a topic that we work hard on, and okay, it's a bit clickbaity maybe, but I'm just bringing it as how to overcome the LFM bias, and I'll talk a bit more about what I qualify as the LFM bias. You'll see. But I think it's an interesting topic and some kind of food for thought for everyone involved in the industry. So just a bit about me, but Samantha did a great job presenting me, but I'm one of the 4 co-founder of Dyze, mainly working in sales, product development, everything related to commercialization and financials. So but with me, we're just I'm not alone actually. So my 3 other co-founders, Phil, JS, Max. Phil and JS are brothers, and Max is just a friend from university. So we all met in universities at university and wanted to actually print a drum, and you'll see here on the screen. We finally, after a few years, managed to 3D print a drum, which was the main goal. And that's why we first bought our first 3D printers in 2010 or 13, something like that. So a funny story. And we started this whole journey as an aftermarket hot-end extruder company. We wanted to improve the reliability of desktop 3D printers, which was starting back then. And we formally started the company in 2015. We're in Montreal. I'm a native French speaker. You can hear by the accent. And I think we're one of the first few players to really tackle on FGF technology. We initially released the first few press releases were in 2018, but we started developing FGF back in 2016. I think almost 1 year after releasing our first few products. Today, I'm proud to say that we're chosen by top-tier global partners. We work with different end users throughout the world, from Japan to Europe and United States and South America. A lot of work happening. Unfortunately, and it might be the case for many of you, but I think that some business cases that are really interesting we cannot share due to confidentiality, and that's something for another topic. But I think it's always hard to get really good business case out there and market them. But we have a lot of great project relying on our technology. Um, just a quick overview of our specific system related to FGF, because we do a lot more. We have filament system, we have motion control system for 3D printers. But here today, I think the interesting thing is to talk about pellet extruders. So our first product released back in 2018, as I said, is the Pulsar. It's a 2.5 kilogram an hour extruder, which is funny because at the time we would market it as a large format extruder. 2 years after that, we were kind of double down on this extruder being more a mid-size or even a small size extruder. If you look at Caracal, Seed, and the other players, still, I think it was really designed for gantry systems. I think LFAM took off in robotics, but this system was initially designed to be mounted on a large format 3D printers. At that time, we didn't even know about robotic that could be used for 3D printing. Years later, we released the Pulsar Atom, which is a very compact and small pellet extruder. It's 1 kilogram an hour throughput. It's really about precision. This product here is what we sell most. I think there's been an untapped market for really small extruders. People looking into FGF not necessarily wanting a big 20, 30 kilo an hour extruder. So here, this extruder can be mounted on quite large 3D printer if you have I would say a stiff enough axis to sustain the weight, because the payload is still 1 kilo, but you can do really small parts with it and rely on the advantages of pellet extrusion. And Scoop here, we're gonna release soon the Quasar, which is a big 15 to 20 kilo an hour extruder. It's currently in kind of beta phase with specific partners, but we might have a final design review during the summer, and hopefully we'll release that product in real this year. And finally, we're now an official, I would say, KUKA partner, KUKA Canada. So basically, we're now selling those kind of fully integrated turnkey robotic cell. It's a new product. We've been doing that for 1.5 years now. We currently have a few of those cells being sold, particularly in South America, where there's kind of demand for it. And I think that Canada and South America is closer than importing from Europe a big seeds turnkey solution or something like that. So we're really proud of that product. Put a lot of effort into programming, making this machine as microwave like as possible. So you don't need to be an expert into robotics. We made sure that it's really easy to use, and it's very targeted towards architects and creative people that just want to print stuff and are not expert into industrial machinery like that. So going into my main subject, the LFAM bias. Wanted to bring some of quotes that we hear quite a lot from different customers when they approach us. First one is like people going, based on our observation, FGF can't really print part with fine details, cannot print support materials or even infill. It needs to be carefully designed. The part needs to be really designed for this process in particular, especially in continuous motion, no stop and goes, and making sure that the extruder can just move without stopping. We also hear that pellet-fed printing results are really poor in surface finish quality, and this is kind of a necessary trade-off. So that's okay, but we will not rely on that technology because we need that kind of neat surface finish on the part that's really, stable if you look at the part. Finally, we also hear sometimes that FGF parts are frequently out of tolerances, bead is inconsistent, and you need to rely on post processing quite a lot for those parts. And I mean, this is kind of not true at all. I mean, depending on the extrusion system, depending on the process, it might be true, but I think that it's kind of creating a problem for us as pellet-fed extruder providers, where we have a technology that's able to actually print parts that are really small, in a really stable way, and that could even be a one-to-one replacement to FFF. And I think that's the focus I wanted to bring today. And this is kind of giving a negative perception of FGF for two reasons. I feel sometimes pellet fed is equated with LFAM, and it's not the same thing. LFAM is like when you print large format parts, relying on different processes, sometimes bigger extruder, and reality is that if you do large format 3D printing, you might require a pellet feeder because it's more suitable for that process. But we have customers using our high flow filament extrusion system on robots printing really big structures. So LFAM is not necessarily FGF. And also, I think there's a lot, and this is a good thing though. A lot of focus being on design for additive manufacturing and material optimization to work with the constraint of some pellet extrusion system out there. But I think people are neglecting the extrusion process itself. And at Dyze, we put a lot of effort on how to control a bit better the extrusion process. And we look at our product and try to improve the reliability of those systems. So you can just do more in a more efficient way and in a more stable way. And you can still focus on DFAM and material optimization. It's always a good thing, but it's not. You need also the extrusion process to be as perfected as possible. And just kind of sharing our own vision here on FGF. So for us, like pellet fed is viable for small to medium format. Here on the screen, you can see really small parts that were printed. We can print smaller parts than we are doing with our higher flow rate filament extrusion system. FGF can be as precise as FFF printing. Here, what you see is a part printed out of our Pulsar Atom, and you can see like the beads are really, really small, and it's really, really precise. So that's something that needs to be accounted for. If you want to print smaller parts, it can be done with the right tool. It's always about the right tool. And finally, the extruder stability must not be compromised. And I think that's the thing that I really want to bring the focus on. I see a lot of case study printed parts that I can see the extruder is not stable, and that's kind of bringing some problems, not only on the part itself, if you look at the mechanical properties, but it's also kind of it's kind of bringing that bias back on the table where people say, hey, I cannot rely on that, it's not looking good, or I will need to rely on post-processing. So how we define extruder stability, it's the ability of the extruder to have the molten plastic maintain its shape, volume, and property after exiting the nozzle. And this is not something you need to define in FFF, because FFF is really, linear. You push a volumetric filament out of a nozzle, and wheels are bringing it down. But in a pellet extruder, you're building pressure. You have less control over the process. That doesn't mean that it cannot be controlled somehow. So for us, we have three, I would say, dimensions of stability. We have the dimensional and volumetric stability. So it's how we can maintain the width and height of the bead. Then we have the flow stability, which I think right now is a concept that everyone's kind of educating people on. Flow stability is not something that I need to define much more. And finally, we have the thermal and viscosity stability. And in some case, I've seen that quite a lot, where you have shear heating in the extruder happening, and then it's going to create some stability issues. And all those three dimensions, those three aspects, needs to work all together. But I think the one that's being neglected is really the dimensional stability. And you can see here example of what I call unstable extruder, and all those. You, if you look like right now, people marketing parts or just kind of talking about case studies, you can see that quite a lot. And in my own opinion, we should overcome this. This is not good, especially the part on the left side. Here on in the middle was a thermal stability issue. And on the right side, it's hard to see, but for Dyze, like if we bench stuff, this is not a pass. If we see a part looking like that, you have under extrusion happening here, you have over extrusion. This is not stable. This would not pass our own bench here. And why is it critical actually to control the stability? Three things: the structural integrity. So if you have that poor, I would say, stability in the part, that will create micro voids that will affect the bonding of the layers. Second, you will ruin your kind of tolerances, and in some application, especially in small with small part, but I think it's true as well in LFAM. Tolerances are really important, especially in industrial applications. And if you kind of have all those instability, it's ruining your dimensional tolerances. And finally, it's important for most cases that visual finish will not be there, right? So I want to just share how we measure the stability of our extrusion system. What is our methodology? My wish here is just to give some insight. Maybe your people are doing it already like that. Otherwise, you can kind of, when developing an extruder or when benching extruders, my wish is that this is kind of a new way to bench stuff, as we are doing when we do flow stability or flow calculation. So basically, it's pretty simple, but we calibrate. That's the first thing to do. So basically, we will print a calibration part with a target mass. For example, maybe 7 grams. We'll do the good old bead measurement to make sure that our flow is calibrated. And when we have that flow calibrated, we will do a repeatability measurement. So basically what we will do is print maybe 10 to 20 of the same parts on the bed and measure the spread and variance of all those parts to find the deviation. And then you simply look at divide this deviation by the mean mass, and it will give you kind of a result, which is kind of the average stability deviation of the system. And here our target, in our case, is 5%. We feel that if we manage in the FGF process to be less than 5, it's a good target. Less than 5 give you less to no visual defects. And sometimes the tolerances required in AM is not like in injection molding or CNC machining. At 5%, we realize that you can still meet your tolerances on a part. And to compare that with filament extrusion, sometimes you're less than 1. I'm not sure if 1 is achievable in FGF extruder, unless you're using a melt pump or something that really control the process. But as you're building pressure, you will not be able to control that to up to a point that it's kind of a linear relation between the feedstock and the actual material extruded that's being extruded from the printed. Yeah, so that's kind of what I wanted to share today.
Thanks, Simon. That was super interesting also to see what you define as success and the targets internally. I have a question to kick things off. I'm curious, and I love that you're pushing the industry to have more normalized targets for what's acceptable and having high standards for FGF, because we know we can get there. I'm curious if you apply that same target across all thermoplastics, or there's some thermoplastics where you might skew more to that 2% and others more to that 5% target.
No, we apply that on everything. What we see though is that depending on the material, we might need to change parts of the extruder. So giving you an example, we have multiple screws, we have multiple barrels, we change parts of the extruder in a way that we can achieve that 5%. But sometimes, yes, because you're gonna have more sure force happening maybe in the extruder, viscosity will change. So definitely the baseline will not be the same, but we always try to achieve that the same quality and stability depending regardless of on the material we were printing.
That's awesome. I have other questions, but I'll turn it over to everyone else while the recording's still going. Does anyone else have a question that they would like to share?
Yes, I have a quick question.
Not a feeling.
Yeah. When you say your extruder is rated for 2.5 kilograms an hour, how do you test or measure that? Is it based on a specific material at a specific temperature?
Yes, it is. I think that's the big argument right now on the market is like, oh, people are testing the bench that flow rate metric that everyone's kind of sharing. Everyone's have a different way and approach. In our case, and maybe it's not helping us sell more stuff, but we have a more conservative approach. So when we say 2.5 kilogram, in true, we can push at 3.5. It's just that we're not bringing the material up to the degradation point for once. And second, we test on what we call the long-term stability flow rate. So basically, it's that point where we're able to run a 2, 3, 5-hour print at that flow rate at a specific temperature that will not degrade the material. Because if you bring, and this was made with PLA, not that we like PLA so much, but I think it was kind of the benchmark everyone would use back in the day, and we kept testing with PLA. But in our documentation, we have tables where we give the same data for many different material. So even though we say 2.5 kilogram an hour, we put out there numbers with PETG, polycarbonate, carbon-based material, things like that. So you can see the difference with different materials. But our methodology here is really about the flow rate that you can get in real life when printing that material reliably. Otherwise, I could tell you that Pulsar is able to do 5 kilogram, but I will bring PLA at the degradation point, and I will get the data point just before I'm skipping the extruder, right?
I see. Thank you.
Does anyone else have a question for Simon?
Maybe I can just join in for a quick question. So what do you think from the market's point of view, like where's the balance between your flow rate, maximizing that, and the market's desire for finer resolution? There's a trade-off there, it just seems, but what's kind of the sweet spot in your opinion?
Yeah, good question. I've seen right now is really kind of splitted. People looking at throughput for business reason will look at throughput and will just rely on post-processing and machining of the part. When people need precision, they don't really care about the throughput and the time to print. I think for them, the main trigger here is to save cost on the material, or sometimes they use funky materials that are not easy to find in filament. So what I've seen from experience, all our customers using, let's say, the Pulsar Atom for precision will not care that much about the throughput. And still, at 1 kilogram an hour, you're still beating any filament extrusion system on the market right now. So I feel that at half that throughput, so 500 grams an hour, you're still at a good balance between production rate and precision.
Thanks.
Does anyone else have a question for Simon?
I actually do have another question. Yeah, so I saw very early in the presentation when you showed us the 2.5 kilogram per hour extruder, and then you talked about the 15 to 20 kilogram extruder that you're currently developing.
Mm-hmm.
What's the big change that almost bumps the flow rate by an order of magnitude? Is it just like
Yeah.
the amount of heaters or the length of the barrel?
Many things. If you look at the two first system, as I mentioned, we initially developed those for gantry system, regular 3D printers. So we relied on stepper motors, right? Because on an integration standpoint, it's as easy as changing your filament extrusion system with a traditional duet boards or whatever board they are relying on in the machine. Problem is that stepper motors are good on they have higher torque at peak levels, but they are not able. They will skip if there are too much kind of overpressure in the system. So moving into the quasar here, we just move into servo motors. We need to be careful because it can break the system, but still you're able to push the throughput by a magnitude. And also, yes, Chris, adding lending the barrel is helping up to a point, and adding heaters as well. Here in the first iteration of the Quasar, the alpha version we had, the bottleneck was really the thermal performance of the system. Servo motor was kind of able to push maybe 30, 50 kilo an hour, but then it's kind of moving too fast for the heaters to melt the material inside the barrel, and it's gonna kind of literally the pellets will go out of the nozzle not melted. So there's always this balance between the motor performance, the barrel length, the thermal performance. It's very high surface. I think extruders seem simple, but if you take the time to look at the performance you want to achieve, it's more complex than it appears. And I think Samantha can share a bit on that too. But yes, yeah, it's multi-factor here, how you manage to push the throughput.
Thank you.
So, can you share, just to clarify, Simon, is the Pulsar intended to be on a gantry system or like a robotic arm?
Yeah, the quasar is for a robotic arm. The payload is 30 kilos. So as of today, maybe like a Thermood machine could take that
Yeah,
extruder, but yeah, it's more targeted for robotic arms.
that's so cool. I am curious, in terms of the calibration cube, we do I love that you call it the sacrificial calibration
Mm.
cube. That's what we do as well. Admittedly, we don't do 20. So that's really stretching that you're, ensuring you have that repeatability. I'm curious because so one thing we struggle with, and maybe someone else wants to chime in here too, that has experience is, there aren't the standards around FGF are still being refined. And so therefore, when it comes to like test specimens and, how we print, so we can show our different technologies and have that common lexicon is really difficult. So I think a lot of us choose the cylinder. I'm curious as to like if you have a specific size every time that you aim for in order to look at consistency, and how you
Yes.
came to identify, those metrics. Besides
Here
just
on the right, this is kind of the specimen we're using for all the stability tests. There are reasons for that. A calibration cube, you have those corners where you have acceleration, deceleration, and in some aspect of it, if we're
yeah,
not fully confident about our system, it's a new development, we cannot add that variable in the process where we have issues with
right.
artifacts in the corner and
Or
pressurization.
salinity and
Yeah,
yeah.
exactly.
Hmm.
So it's not that we like vase mode so much, but it's a great way to remove variables. So we're
Yeah,
printing cylinders like that because we can just print them in vase mode. So it just on a kind of DOE standpoint, it's kind of better to remove any variables that will look further down the road. When
yeah,
we're happy with stability, let's say we develop a new extruder, we're happy with stability, then we will start doing those kind of squares where we'll look and focus on the corners because it's giving us data on all what's the lag on the system. How
yep.
can we control that lag? And can we control that lag actually?
And then for the cylinders themselves, like I can't tell, do they have a solid bottom layer?
No, they only have like a small brim, and then we
Yep.
start doing the cylinders, but they are open-ended cylinders.
And are they always the same size and height? I would love to commit as an
Yes.
OEM to doing the same test as you time.
Yes,
So
I think those ones are 7 grams. I can't remember why 7 grams and not 10 grams,
yeah.
but that's kind of the metric we use. So every
Mhm.
cylinders, every material, always the same cylinder, same size, 7 grams per cylinder.
So
Um,
you go by weight and not necessarily the size.
yes, we
Interesting.
do. As I mentioned, the first cylinder we measure the size because we want to make sure that the flow
Mhm.
rate is spot
Yeah.
on. But then we move into mass because for us
Ah,
stability, we have, because it's not linear process, it's a pressure,
right.
we it's better to rely on the mass that's been extruded than the dimension accuracy. It's giving us more it's giving a it's in the past, that's the way we approach it. Now we're refining bench, and now with visual cameras we try to
Mhm.
actually measure the bids, it's the bead dimension. I think this is a better way to measure stability, but if you don't have that uh, kind of high level labs equipment, you can still work with just specimens like that and measure the mass
Mhm.
of each.
Yeah, that's a really awesome approach. I like that a lot. Oh, Dan has a question. Yeah, cut me off, Dan, because I'm just
Hmm.
enthralled with
No, no,
seeing.
no, it's fine. It's not so much a question, but it's a really good point because we found some issues with our pellet extruder last summer and how benchmarking wasn't really like the traditional benchmark materials and shapes weren't really feasible for telling us exactly what we wanted to know for these pellet ones. So we found that I have a fairly small one. It's a direct 3D pellet extruder. It doesn't have a lot of pressure. And so we were finding that what was optimal, quote unquote, for one layer height was not for another. So one of my students found like if he actually just kept increasing the Z height as he was printing what was supposed to be a cube, it would just make 100% fill like rectangular shape thing. So I was wondering if you're doing any kind of like optimizing based off of your layer heights as well, or calculating based off of back pressure. Because yeah, that was a surprise for me, was just how wrong it was if we had a really small layer height and then like you were changing all these numbers, but really it was like completely overcorrected.
Yeah, I love that. Then there's something there's a I would say we observed something throughout the years, and we haven't yet kind of figured out why it's happening. I think it's due to back pressure. Um, if we have layer height less than the nozzle, or less than 1.5 the nozzle size, uh, and we saw this with really clear PLA or PETG, we would see those swirls into kind of the parts happening. So it's or we would see gaps as well. It's like if the reactive time that you need for that high precision layer height is too much for such systems. So the rule of thumb that we say to customer is don't try to go less than 1.5 the nozzle on the layer height, otherwise you'll see visual defects and it will create problems. So I think it's a bit in line with what your student observed. We haven't yet find why or how to control that, but I think that if we're able with the extruder and in your extruder to release the back pressure, it might help, and also have less lag. There's this kind of the pressure advance on the machine can help. I don't know what machine you're using, but pressure advance calibration can help quite a lot because it's gonna kind of change the RPM of the screw to account for acceleration and deceleration on the axis of the machine, and that can help because if it's not calibrated, when the extruder and the axis will kind of move at a corner or do some kind of deceleration, it will stop the screw, and then the time to bring the pressure back in the extruder might create some issues. So, and I think it's happening way more in smaller layer heights. Yeah.
Yeah, it definitely seems to be. I haven't decided what the best course of action is for us for future, but it may be like we just print like if it's our nozzles are pretty small because it's a pretty smsmall pellet printer, but if we were going with like a 0.4 nozzle, we can print with a 0.8 height, but then just over extrude to make sure the bead is like 1.2 millimeters across, and it seems to be okay there. But yeah, it was a surprise to us. It was like, oh shoot, we weren't calibrating what we thought we were at all for the last 2 months. So.
Yeah, and there's this change of paradigm as well. When you come from filament-based printing, there's much to learn in this process here. A lot of education, and you need to kind of change the way you approach slicing and calibration and things like that.
Yeah. Cool.
Can I
And
ask
one
a
other final
question?
question is just actually like you seem to be still using a lot of like the blue painter's tape for these demos. Is there a reason for that?
Yeah, I think that the pictures here are from our R&D department. I think that those guys love the blue tape. It's just easy to remove that, and truth to be told, it's sticking quite well on that. Tested different types of surfaces, garolite, PI sheets, glass, and at the end of the day, what works best is the blue tape and plywood. Actually, so
plywood.
It's not looking great in a marketing support document, but in real, that's what works best.
Right, thanks.
Can I ask a question? Just listen to the conversation and kind of list to some of the questions on my mind. First, about with your slicer, have you looked at using machine learning? Because one of the things in my mind is that the slicers assume the beads are rectangular, because in slicer it's rectangular. but the bits are by itself, they are not rectangular. And I think that's one of the reasons why there is issue with the printability, especially when you come to the height of the of your print, because when the bits come out, they are never rectangular. Have you looked into that? I was just thinking about if machine learning can be one of the solution in the slicing process to reduce the issue.
Yeah, definitely. I think we're looking forward to have machine learning processes in every aspect of what we do, material, but also slicing, things like that. We have not used that yet. We rely on slicing on standard slicers, but also partners such as Adexis. That's more on the robotic side of things, and their approach is better with pellet-based system that rely on pressure and kind of it's not as linear as filament-based system. But here one of the problem I think is not much on the slicing more than the all because with filament system you can monitor like the actual filament that's being extruded compared to what the slicer and the G code is commanding, right? With FGF, you cannot do that. So what you need is some kind of sensor that can either measure the pressure or the torque of the motors. You need new data points that you can use to compare with what was commanded in the G code. And yet again, the G code is really made for linear extrusion. So we're not yet at a point, I feel, on a software standpoint, where we're fully grasping the ideology of FGF. But I think there are really good software company working on that right now, and I'm confident in the near future we'll have more reliability on the kind of G code and the path planning and toolpath, and how you slice your parts for pellet feeding.
Okay, thank you. Just the other question: how do you determine the printability of your plastic? Because when you look at the flow or the viscosity of each plastic is different.
Yeah.
And then when you need to print from different one, how do you determine what pressure you're going to use, what
Yeah.
what speed you're going to push out your pellets?
So
Do you use any standard
we have
or
some
you
we have
just
some
get
kind
out?
of
Yeah.
we have some kind of bench. So we do open air extrusion. We extrude on a balance, and basically we're kind of reporting the flow that way, and we are monitoring temperature data, and we do iterative tests. Right now it's mostly automated nowadays, so for us it's quite easy to get a new material, put it inside the extruder, run the test, we collect the data, and that way we can do some kind of material characterization. I think guys at Juggerboard, they have a even more automated way of doing that. But it goes really into collecting data points when you run material, and if you can automate that, it's making it way easier. But there's no like shortcut. I think the other thing we do is we work with material suppliers that use our system, and they do material characterization on their side. So then if customer buy that material, they already have like a library of material from the compounder.
Thank you. Just one more last question. Sorry. I'm just thinking about do you have an issue of hair gap in between when you do your printing? Because when you have the beads going through, and usually because of the shape of the bead, there's usually a gap in between.
Mm-hmm.
I wasn't there at the beginning of the presentation, so I
Yeah.
just woke up to be here. Yeah. Just looking, how do you solve that ear gap? Some people use
When
um,
we have air gaps, it's just because the material is not dry enough. So we're really careful on drying all the material we have, even if it's not hygroscopic material like PLA. we still kind of dry them, and we remove 99% of air gaps that way. The rest sometimes is due to, if it's a filler-based material, sometimes you have air gaps because of the way the material was compounded. But if I look at virgin material that we extrude, not really having air gaps issues. The only air gaps we might have is if we don't have, as I mentioned here you can see in the middle, it's an extreme case, but if we have like instability, which is the case I wanted to prove, is you will have air gaps. But if you're able to stabilize the system and calibrate it, you should not have those air gaps.
I was wondering actually if I could hop in with a comment here about the air gaps. Over the summer, I was actually using FGF to print soft robotics, so like pneumatically airtight components that could move when they were inflated. And maybe to echo like Tosin's comments, I was having really notable issues with printing airtight components because of the interlayer voids that would be left behind between printed beads, and we had to do basically a lot of iterating on the aspect ratio of the printed bead in order to try to eliminate those gaps so that we could prevent leaking. And uh, this loops back to what Dan was talking about too, actually. But we did find that like while reducing the layer height would kind of compress these interlayered voids a little bit better, we would find these kind of compressibility and back pressure issues that kind of brought us back to the issue that he was talking about, where it would actively change the flow rates that we received over time with this like kind of transient response. And it was really interesting. But yeah, also definitely keeping an eye out on like print porosity and even how that interacts with retraction points as well. It's all very interesting stuff.
Yeah, thanks, Luca. It's interesting insight that you brought. One thing that I have in mind right now is that I think people are not, and even at Dyze, we're still not monitoring that as much. But the back pressure is really something that's creating problem in such system, I think, and air gaps might come from back pressure. Too high back pressure will, because the air will try to go away, and if it cannot go up, it's gonna go down as you print, and it's gonna create air gaps in the system. So and it's something that we're looking right now, is how the air is kind of moving with the pressure inside the barrel, and where can you kind of get that air out of the system. So yeah, interesting point.
I'm curious. I'm gonna go back to the cylinder because I'm like a honey badger when I'm starting to think about something. I'm curious if you guys have thought about other test articles or artifacts that might be helpful in terms of starting to create a standard within the FGF community that we should all center on.
Yes, we started to work 2 years ago, but it was put on the ice for now due to just kind of resources. We started to work with NRC, the National Research Council of Canada, that do a lot of work in the train industry with FGF 3D printing. Really interested into getting a standard out there, just so everyone could fit on that standard. And at the end of the day, it's not more about Dyze or Re3D. It's more about how customer can find and compare a different system and solution. If we all have different ways to analyze and kind of bench our system, it's not helping anyone. So we had that work, but we right now no new development on that. But we had a few ideas that I could share with you, Samantha, if you want, about what were the core metrics to look at and how to deal with the test as well, because if you have a standard, you need to also give the kind of the protocol to test. So yeah, we drafted
Yeah, I know
something.
Towson's universities thought about this too, in Australia, and others on this call. Yeah, maybe that is an opportunity as we think about the user group long term. Maybe we have one user group just kind of dedicated to that topic where we can all share, whether it's recorded or not. And prior to starting this recording today, for the other participants, Simon and I were chatting about, alignment with our companies and others on teaming on grants. So maybe there's this is a global topic, so maybe there is some international funding for us to align as we help try to shape the conversation in the industry. I think at this point, because we're coming up on time, I'll turn the recording off in case there's any last questions that someone had. But know that before we do that, if you have a suggestion on a speaker or someone in the community that we should pull in, I think we all really value getting the introductions and perspectives that each other has. So please feel free to forward them to Michael or myself, and or if you have suggestions just for content as we're thinking about our peers and who might be able to provide a great insight. So we'll go ahead and turn the recording off.